voice? Can you hear my voice? Yes, girls, are you with me? So we have started chapter number 12, that is Broadband Network Management, in our face-to-face lecture this week. We have discussed about the Broadband Network and ISDN, that is Integrated Services Digital Network. And we have seen that both of these are the multimedia networks, and we have two types of ISDNs. The first one is the narrowband ISDN, and the second one is BISDN, that is broadband ISDN. And narrowband ISDN is the low bandwidth network, and BISDN is a high bandwidth network, and it transports very high data rate signals. And then we have seen that there are three types of protocols that we are using. The first one is ATM, that is asynchronous transfer mode. And then we have SONET or SDH, that is synchronous optical network and synchronous digital hierarchy. And the third one is MPLS, that is multi-protocol label switching. So we have discussed M1 interface, ATM transmission groups, M2 interface management. Now we have to start from M3 interface. So here M3 is the management interface between the private network management system and the public service provider network management system. It allows the customer to monitor and configure their portion of public ATM network. So networks show the typical configuration, that how a customer will interact with the public service provider network through carrier management system. So as you can see over here, there are two classes. We have class 1 and class 2. So there are two classes of M3 requirements. One is the status and configuration management, that is class 1. And the second one is virtual configuration management or virtual configuration control, that is class 2. So in class 1, requirements are those which a public network service provider offers to the customer. And these includes customer performing monitoring and management of configuration, fault and performance management of a specific customer's portion of public ATM network. And this service is offered only for PVC configuration. Now class 2 service provides greater capability to the user. The user can request the service provider to add, delete, or change the virtual connections between a pair of customers' UNIs. And an example of this will be the customer wanting to establish a new virtual path or increase the number of virtual circuits in a given virtual path. So we have customer network management CNM agent, which resides in the private service provider's NMS and provides the M3 service. So the service is limited to the portion of public service provider's network that the user circuit traverses. And if the user circuit traverses multiple service providers, then we have a separate interface with each provider is needed, and CNM sends the request to the carrier management system, as you can see over here in this figure, that the CNM sends the request to carrier management system, which acts as an agent to the CNM, and the carrier management system then invokes the request on the network element, that is NE, or other NMS and returns the responses to the CNM. So the requirement for M3 and M4 are specified as mandatory or required, conditionally required, and optional. So class 1 requirements are mandatory and class 2 requirements are optional. Now here we have ATM relationship in TMN layered architecture. So the management of public ATM network is actually the responsibility of network service providers, that is carriers, and PTT companies, that is postal, telephone and telegraph companies. So they have the challenge of not only managing the public network but also keeping up with new technology. So to help this process, we have ITUT, which has defined a 5-layer model of operations, telecommunication management network, and the relationship of ATM to TMN is shown in this figure. So the top 2 layers, they are the business management layer and the service management layer, which deals with the business and service aspects of TMN and are not addressed by the ATM forum. The element layer, that is EL, contains network elements, NEs, and the NEs specific to ATM technology are components such as ATM workstation, ATM switches, ATM transport devices, etc. So the element management layer, that is EML, they manages the network elements. And the network management layer, that is NML, has the responsibility to manage the network either directly or through EML. Now see this figure, the next one. This figure shows the dual view of M4 interface. Now both views are present in the architecture across M4 interface plane. This is the conceptual view and the physical connections can be the same for both views. Now in NE level management architecture, the NMS environment consists of one or more network management systems, directly interfaces with the ATM NE and manages them. So there is a single M4 interface between ATM NE and the NMS environment. And this figure shows the links between network elements, but the NMS directly communicates with each ATM network element. So in an actual implementation, it is likely that the NMS is interfacing with another NMS, which is managing the network element, but can still present a network view to the higher level management system. Now in this figure, we have an example of network view management physical configuration. It consists of 2 ATM networks, one a single supplier subnetwork and other a multi-supplier subnetwork. Each subnetwork has its own sub-NMS, which is managing its network element, and in single supplier subnetwork, which is shown on the right side, the sub-NMS has only an ATM NE view. And in the multi-supplier subnetwork environment, which is shown on the left side, the sub-NMS is presented only an ATM NE view. So although it may actually be communicating to lower level NMS of each supplier, this is similar to the manager of manager architecture. If you remember, we have discussed about MOM architecture. So this is explicitly shown in this figure, both sub-NMS in figure 12.16, that is the previous one. So this is shown in next figure, this one. So M4 network element view requirements and logical MIB management information base ATM forum M4 network element view specification support PVCs. So based on the OSI application model, the specifications are confined to configuration management, fault management, and performance management. So basic security features are also included to ensure the authorization and authentication of the user and the protection and privacy of data, while M3 interface responds to the queries. Now this is ATM DXI Management. DXI stands for Digital Exchange Interface Management. So Digital Exchange Interface is basically an interface between a digital terminal equipment, that is DTE, and a digital circuit equipment, that is DCE, that connects to a public data network. So in ATM network, the public data network is a network of ATM switches. Now this figure shows an ATM DXI local management interface. The ATM LMI basically defines the protocol for exchange of information across DXI interface, and it supports DXI, AAI, and UNI specific management information. So the LMI protocol supports the SNMP management system and ILMI management entity, that is IME, running on an ATM switch. So the ATM DXI LMI MIB supports IETF ATM MIB and the ATM Forum UNI MIB. Now here we have simplified MPLS network. MPLS is multi-protocol label switching, and it is a fast emerging WAN technology that replaces pure IP and ATM networks. It combines the richness of IP and the performance of ATM networks. So MPLS network, this is one of the important development in WAN transport technologies in the evolution of MPLS protocol from IP and ATM. So an IP-based network is feature-rich because of its extensive implementation and compatibility with Ethernet LAN. It routes the packets intelligently, and it is slow in performance as it has to open each packet at layer 3 label to determine its next hop and its output port. So the simultaneous transport of real-time and non-real-time traffic is difficult. And in contrast to IP, the ATM protocol is a high-performance cell-based protocol, switching cells at layer 2 level, and it is capable of handling real-time and non-real-time traffic simultaneously, and it is superior to IP-based networks. So it has been deployed extensively in wide area network, and its address incompatibility with popular Ethernet LAN along with difficult end-to-end circuit provisioning has limited its usage at the customer premises network and therefore related applications. So we have MPLS protocol, which evolved to combine the richness of IP and the performance of ATM networks. It is deployed in convergent network for broadband services, handling real-time and non-real-time traffic simultaneously. Therefore, it achieves high quality of service transport, and it can be deployed in legacy network of either IP or ATM base. So we have a simplified representation of MPLS domain network with an Ingress MPLS router and MPLS router. This shows the MPLS header named label, which is added between layer 2 and layer 3 to the packet or cell delivery by the external network. Now, in conventional IP, forwarding is done based on the packets with the same FEC being sent to the next hop on the same port. So FEC is determined by comparing the longest match for each packet destination address. FEC is forward equivalent classes. Forward equivalent classes. So this is done for each packet at each router. As you can see in this figure, this is IP packet forwarding based on FEC index table. So the incoming packets 1 and 3, they basically generate the same FEC and are transmitted over port 3. So packets 2 and 4, they generate FEC2 and exit out of port 4. Now in MPLS, the assignment of FEC to packets is done once at the ingress router. So all the packets that belong to a particular FEC, they are assigned the same path, or we can say paths in case of multi-path routing, leaving the node, and this is shown in this figure, that is MPLS packet forwarding based on FEC index table, figure 12.22b. So in MPLS, the assignment of FEC to a particular packet is done just once at the router and is encoded in a short fixed value length in the label. So once a packet is assigned to an FEC, no further header analysis is done by the subsequent routers, and all forwarding is driven by the labels. So the label is sent along with the packet, and at subsequent hops, the label is used as an index into the table. So it specifies the next hop and a new label. The old label is replaced with the new label and the packet is forwarded to its next hop. So what we have an MPLS forwarding paradigm which has number of advantages over conventional network layer forwarding. For example, MPLS forwarding can be done by the switches that are capable of doing label lookup and replacement, but they are either not capable of analyzing the network layer headers or are not capable of analyzing the network layer headers at adequate speed. So some MPLS routers, they analyze a packet network layer header to choose the packet next hop, and others are they determine a packet precedence or the class of service. So they may then apply different discard thresholds or scheduling disciplines to different packets. So this is a network which includes both MPLS and ATM. Here we have a virtual circuit routing table, and all packets take the same path and arrive in the same sequence in the virtual circuit, because this is an ATM also, and in ATM we know that we have a connection oriented service, and a virtual connection is established and the packets follow that connection, and the order of packets, they are same. Now packets in a session take same path. This is VPVC, that is virtual path virtual circuit, and after initial setup the latency is reduced, and both real and non-real time traffic, they are handled simultaneously. Now this is MPLS traffic configuration. This is concerned with the performance optimization of operational networks, and it includes the measurement, modeling, characterization, and the control of internet traffic to achieve specific performance objectives. So a major goal of MPLS traffic configuration is to facilitate efficient and reliable network operations while simultaneously optimizing the network resource utilization and the traffic performance. And the aspects of TE that are of interest concerning MPLS are the measurement and control. Now in this figure, we have MPLS IP without tunnel. It illustrates the IP routing with interior gateway protocol that we call as IGP without traffic engineering and tunnels. And it illustrates the interior gateway protocol network topology with TE and tunnels implementation. So the respective routing tables for R1 is shown here. This is the routing table. This is MPLS IP with tunnels. Here we have the routing table in the label switching router, that is LSR R1. And the LSRs R4 and R5, they are directly reached from R1 through tunneling. And the transit time delay is low and the throughput is high, as the intermediate routers in the tunnel behave as pass-through. So the path from R1 to R4 now exits out of the logical port T1 and has the next hop as R4. So there are two merits shown for educational purpose. It is 3 if no absolute value for the tunnel path metric. It is an absolute value in our case chosen as 1, and the value of the metric is 1. So for the case of LSP from R1 to R5, the corresponding metrics are 4 and 1. This is MPLS TE. TE stands for Traffic Engineering. Traffic engineering is concerned with the performance optimization of operational networks. We have control capabilities offered by existing Internet Interior Gateway Protocol. So a popular approach to circumvent the inadequacies of a current IGP is through the use of an overlay model such as IP over ATM or IP over frame relay. So the overlay model provides additional important services to support traffic and resource control. So it includes constraint-based routing at VC level. Then second, support for administratively configurable explicit VC paths. Thirdly, we have path compression. Fourthly, call admission control functions. Fifth, traffic shaping and traffic policies functions. And sixth is survivability of VCs. So these capabilities enable the actualization of a variety of TE, that is traffic engineering policies. For example, we have virtual circuits that can easily be rerouted to move traffic from overutilized resources into relatively underutilized ones. Now this is label switching router. A label is basically a short fixed length locally significant identifier which is used to identify FEC. So the label which is put on a particular packet represents forwarding equivalence class, that is FEC, to which that packet is assigned. So MPLS label is a 4-octet or 32-bit along header, and this is shown in this figure. So it comprises of 20-bit label, 3-bit experimental, and 1-bit stack indicator, and 8-bit TTL, that is time to live information in that sequence. So the label is assigned by a downstream router. We will see this later on. And the experimental bits, they are used to describe the class of service such as QoS. So the stack indicator bit is 0 if it is the bottom of the stack of labels, or else it is 1. So TTL basically defines the maximum number of hops Now this is label generation. That is the label generated by downstream SLR. So the packets being sent from RU to RD, they do not imply either that the packet originated at RU or that its destination is RD. So they include packets that are transit packets at one or both of LSRs, and this figure shows two upstream LSRs, that is RU1 and RU2, that communicate with the downstream LSR RD. Here we have packet L1 with FECF and packet L2 from RU2 belonging to the same FECF, which arrive at downstream LSR RD. So labels L1 and L2 are outgoing labels of RU1 and RU2 respectively. They are RD's incoming labels. Since they belong to same FEC, they exit the same port of RD with the newly assigned labels L3 and L4 to the next hop from RD. So L3 is assigned by LSR, that is downstream from RD. So we can say that MPLS offers the best of IP and ATM network and is well suited for multimedia broadband network. It is currently being deployed by broadband service providers at a rapid rate. Now here we have LSP, LSR and label. So this is called label distribution protocol, and label in an MPLS network. An LSP, it comprises the path from ingress to egress router of an MPLS circuit. As you can see in figure 12.29, it is made up of one or more entries in MPLS switching tables in each of the LSRs along the LSP path. Now each LSR has one input label assigned by the upstream LSR and one or more output labels based on whether a packet is unicast or it is multicast. So we have an output label and is interpreted by downstream LSR as an input label locally. So an input label is used in an LSR to determine the output labels and the output interface based on LSP. So the output label, it is tagged by LSR R2 and is interpreted by LSR R3 as the input label and is used to tag the output packet with output label and transmit it on output interface. So the input to output relationship is derived from cross connect table of LSR. Now this is MPLS OAM management. So in MPLS network, the data planes and the control planes, they are different. Data plane basically carries the traffic and is used for MPLS OAM, that is operation, administration and maintenance. So OAM packets follow the data path. Yes, Latifa, what happened? Any problem? Yes, Latifa, any question? So what we have MPLS layer, that can be visualized as the layer position between layer 2 and layer 3, and therefore we have OAM, that is operation, administration and maintenance of MPLS, which needs to address both the networks, that is ATM MPLS and IP MPLS. So OAM in ATM MPLS network is addressed and compared with IP MPLS network, and OAM in IP MPLS network is covered in the next section. We'll see them one by one. But first of all, we will see the fault management of LSP. So what happens when an LSP fails to deliver a packet to LSR? The failure can be due to several reasons and cannot always be detected by MPLS control plane. So LSP failures require testing of specific packet flow besides the failure of network infrastructure, because in many instances packet flows may get interrupted without network failure. So in this figure you will see various kind of fault scenarios. We have A and B. They are the intended receivers for A dash and B dash respectively. So fault scenarios are firstly simple loss of connection, then there is a misconnection, or there is a swapped connection, or mismerging, or loop unintended replication. So in order to ensure that LSP failure is always detected, it is important that the OAM packets used travel the same path as regular data packets, as the data plane always interacts with the control plane. So there are two distinct methods which are specified in the standards like ITU-T, International Telecommunication Union Telecommunications, and IETF, that is Internet Engineering Task Force, for detecting the LSP fault detection and recovery. So we have discussed about MPLS network in detail. Let's switch over to optical network. Okay. So in this optical network, we will discuss about the SONET and SDH. So basically, optical networks which uses WDM technology, it is the most flexible and diverse mode of transportation. WDM technology can solve the enormous traffic growth problem evolving through multiple technologies using multiple protocols. So for current high-end transport, we can use IP, ATM, MPLS, or TDM wrapped in SONET or SDH frame and transported over the optical physical layer. So in the course of time, as IP MPLS technology advances to handling the real-time and non-real-time QoS, as the ATM does, the IP MPLS can be transported directly over the optical physical medium. and without SONET SDH intermediate layer. So we have WDM network management, which comprises of network elements and the network configuration, and NEs are similar to the ones which are named as amplifiers or regenerators, add drop multiplexers, and optical cross connects. So optical configuration relates to the parameters such as network discovery, connectivity, protection path, etc. So in this chapter, what we have discussed about the ATM technology, which has brought the private and the public switch network services closer together. And they overlap each other. Because of that, the network management function overlaps. Then we have discussed about MPLS network, which is evolved by using good performance of ATM and the rich features of IP, and the basic principles of label switching and LSP routing using LSRs. Then we have seen the optical fiber medium, which is used to extend the wide area network, and these are called MAN feeder networks and SONET or SDH ring network. So SDH is a digital hierarchy, and SONET SDH are used as physical layer protocol for optical transport of information over long distances. So this is all about chapter number 12. We have still time. If you have any question, any doubts, you can ask. Yes, Ms. Latifa, you had internet connection problem. Okay, no issue. The session is recorded, so you can hear the session later on also. So this is all for today. If you have any question, you can ask. Otherwise, we will meet in next face-to-face lecture, and we will cover chapter number 13, inshallah. Till then, take care all of you. Assalamu alaikum.